yeah, I'm gonna talk about LLMs in general. I'm gonna give a quick demo on our hardware. Talk about transformers. I'm gonna talk about how we got to these kind of speeds, and then I'm gonna kind of sum everything up. So you've been hearing a lot of the news recently, and people have been asking, like, are LLMs the next revolution in computing? And if you followed the hype, then you probably heard a lot of things. People talk about chatbots or coding assistants. But I mean, you get uses from everything from medical to search to support, data analysis, education, and a million more that have yet to be unlocked. Essentially, the key here is that in order to get to all of these like really impressive and cool use cases, speed is absolutely key. And it really needs to be real time for many of these in order to be actually useful to humans. Like if a doctor is looking at if they need to get like a second opinion on some kind of diagnosis that they're making, if it takes even like several minutes, like the average doctor's visit is like 10 to 15 minutes. So if it takes 5 minutes, or if it takes like a couple minutes even to get your response back from these LLMs, then it's not that useful for them. So speed is absolutely key for a wide range of use cases. And once we achieve that speed, there's going to be a million more use cases that have yet to be unlocked. So let's kind of think a bit about previous computing revolutions, right? So you have your like graphics user interface with the Macintosh. We got to smartphones, and things got more intuitive. And they kind of transformed computers from very specialized machines to personal devices that literally anyone can use. So just as like the internet simplified access to information, many of these language models like simplify things in the way that you can search a research paper instead of going to the library. These language models are going to totally change how we interact with data, with the internet, with other computers, with other people. It's going to change our society. And so, but none of this was possible until algorithms got fast. The Macintosh could never have came out until the Motorola 68K CPU existed. And the same for large language models. In order to like bring about this revolution, we need the next hardware revolution. And that's where Groq is. That's why we're here. So alrighty, so let me pull up my really quick. All right. Can you guys see that? Can you guys see the Groq? Can you guys see the prompt here? Hello? Okay. Does someone have like a cool question or something that's been burning at them?
Why is the sky blue?
Why is the sky blue? Okay. And it is fast. So as you can see, we're getting, this is the 70B model, and we're getting like 300 tokens per second. And like if you can literally take a look, you can compare that to say, you can compare that to OpenAI or Bard or any of these other models, and it's just insane how much faster it is, how much faster running language models on Groq hardware is, the real impressive thing is just the absolute difference in latency here, and that's really what's going to unlock like all of these new use cases and all these new impressive things coming down the pipeline. So, alrighty. Cool. So, so language models, at least the most popular ones, are pretty simple. So they're just neural nets that are trained to predict the next word. So you put in some words and you get out a probability distribution over all the possible next words. So there is there's a it's an extreme combinatorial complexity if language is treated as just a probability distribution. But because the grammar rules, not every word is equally important, and the local context matters a lot too. There are a lot of tricks that these language models like kind of learn to pick up on, besides just building their own world models that are really impressive, that allow them to actually predict what the next word is. And so essentially the big development that has led to like very good results recently has just been this model called the transformer, which it's only maybe like 6 years old, but it just turns out to work very, very well for these types of problems. And so specifically the transformer that you've all heard about is specifically autoregressive transformers, which means that they essentially you take the output from the transformer and you put it back into the input in like an autoregressive process. And so you can predict the next word, you can predict the next word after that, and keep going and keep going. So the main mechanism that they use is a mechanism called attention, which basically determines which of the input tokens matter when predicting the next token. And you can think of attention like a fuzzy dictionary. Like in a regular dictionary, you have the query, which is like the value you're looking up. You have the key, which is the value you're comparing against. And then the value, which is like what you want to return from the dictionary. So you have this key value store, and you want to return the value associated with the key that's equal to the query. In attention, it's similar in that we want to return this value. But instead of an exact match, we want to return the values scaled by how much their corresponding key matches the query. And you can think of, as you know, you can think of the dot product like a similarity metric, kind of like cosine similarity, like u dot v is the magnitude of u times the magnitude of v times cosine of the angle. So in that kind of similar way, you can think of the dot product as a similarity metric. So when you do this q times k, the query times the keys matrix product, in a sense, you're getting the similarity between each query vector and each key vector. And so we can't just use that to look up what we're after, though, because it would improperly scale the results. So we need to take the softmax first, which essentially gives us, because the softmax scales everything between 0 and 1. So just as you, in the dictionary, you basically find which of the keys matches the query, and then you use that index to look up the value. Here, we're using the softmax to kind of get the indices or the scales by which we want to return the values of. And then so we take the softmax and multiply that by the values. So you can see here, the words in orange are scaled up by the attention, and their values are in a sense chosen to move to the next layer for further processing. And so, yeah, let's take a look at the actual like compute of these operations. So most of the expensive matrix operations are in the feed forward and the attention blocks. So we'll take a look at the multi-headed attention mostly here. So in the attention, that would be these ops specifically. And so we got some linear transformations for calculating Q, K, and V. And then we have some both attention matmals here and here. And then we have a final linear layer as well. And so these linear layers, like they use up compute. The compute that they use is proportional to the sequence length of the input, which is still not great. We don't want to see that. But this QXK matmal is even worse in that it's quadratic to the sequence length. This is not great. We don't like this. And so, but there are some tricks. There's actually some tricks that we can use to remove this quadratic dependence here. And so that's the KV cache. So Llama-2 implements a KV cache by default, actually, which is really great. And so essentially what we're doing here is because the attention of each token only depends on the previous tokens, we can actually cache the previous token's attention and then only calculate it for the single new token. And this brings the size of the Q matrix down to a constant so that it no longer depends on the size of the input, which is really, really great. Love to see that. This is propagated through the entire attention mechanism, which saves us a ton of compute whenever we are generating new tokens. So as you can see, the new QXK mapmol, we're doing far fewer operations to generate a single token. And this scales for, this works for all 80 layers of Llama-2. And so basically we can, So as kind of talked about before, there's a lot of matrix multiplications in these attention operations. And part of the reason that Groq does so well on transformer models specifically is that our MXM, or matrix multiply unit, is really, really powerful. At least compared to GPUs, there's a lot less movement that needs to happen between memory and compute. GPUs are specifically good. They're specifically good at batching, like doing SIMD operations. But LLMs are a serial problem in that we need to compute the first 99 tokens before we can calculate the 100th token. And serial problems like this cannot really be batched effectively because you have to auto-regress, you have to go through. And so that gives us a huge advantage. And another reason that we tend to do really well is that calculating each token requires, we have to reload the weights a lot of times, like back and forth. And our memory bandwidth, which is like over 80 terabytes per second per chip, provided by our SRAMs, just blows NVIDIA out of the water, which is really awesome. And we're on our way to like orders of magnitude even more improvement just on the software side. Like tricks like batching, pipelining, intdate, C2C, runtime optimizations, faster sampling, like all kinds of things will bring us we started off 10 tokens per second per user in July. We got to 65, 100, and then in September we got to 300 tokens per second per user. And we're expecting to get up to 48,000 tokens per second per system in the next quarter. Which is absolutely insane that we're like seeing these numbers, but there's just so much performance that is still left to eke out of the hardware. So so large language models are obviously large, it's in the name, and each Groq chip only hosts 220 megabytes of SRAM, so we do need quite a few chips to fit these models. So for example, for Llama-2 70B, we need 8 Groq racks, which is 528 chips in total, to run the 70B model compiled with a 4K sequence length. And there's some other changes that we did have to make to just like the way that we like run these models that are a little different, but end up providing the same result as that are actually mathematically equivalent to the original implementation by Meta of Llama-2, and I'll get into that a little bit more in a minute. But so essentially, there's some modifications we have to do to the PyTorch. Then we export to Onyx. Then we do some quantization steps. Then we do some partitioning, and then we compile and deploy. At the moment, this takes a few days, and we're constantly automating and improving this process. For most models on Hugging Face, this is totally automated already. For these larger models, there's still some tweaking and stuff we have to do. So what are some of those tweaks? So for Llama-2, we do have to like de-nividify the model. So that kind of entails removing any CUDA specific code, doing and removing any GPU specific optimizations, like replacing the shard and linear layers with normal layers, swapping the dynamically sized KV cache for a statically sized KV cache, and swapping any other ops not part of PyTorch for their equivalents. So next, we need to do an Onyx export. We need to export to Onyx. So this is actually pretty straightforward. Exporting and running, basically just exporting and running shape inference and running the typical Onyx optimizations. So critically, we do quantization at this step. We will convert everything we can to FP16, and then we'll convert everything we can get away with to int8 or FP8. And this is still, of course, an active area of research. We're doing a lot of development and testing using the state-of-the-art quantization methods like smooth quant and quick to determine the best trade-offs here. So then we partition the model depending on how we want to distribute the ops across our system. So yeah, next, so after converting to Onyx and partitioning, we're then ready to compile. We can distribute this process across multiple threads and even multiple machines. And while it does use a lot of memory at the moment, it should complete in just tens of minutes, which is pretty great. And so yeah, it's an example that's specifically for like that would be for like a Llama-2 7B model targeting a single Groq rack. And then so yeah, finally we will execute using our runtime on the chip. And we have a custom instruction engine that handles all the features that you're used to from OpenAI and others, like top P, top K, token limits, etc. So yeah, next I'll show you a quick demo video. So yeah, besides the bring up, basically, well, yeah, we'll show you so bring up is ready. So we did the bring up, and then now we'll start processing some prompts. And this is using the script that you guys have on your machine. And so it's loading the IOPs, verifying the C2C links, which takes like a couple seconds. And then it will actually start running this. And yeah, so you can see that we're getting like over 300 tokens per second here. So really exciting speeds and really cool results. So nice. Okay. There we go. And so yeah, there we can see what kind of like over 300 tokens per second, which is great. So I guess as a quick recap, in your hands right now is a state-of-the-art system that puts you years ahead of anyone else on the planet. Like imagine getting access to an Intel 4004 in 1930. Like that's where you guys are right now. So honestly, we're just excited to see what you guys do with it, what you can come up with. And so, yeah, thank you.